Hi everyone. In this video I'm going to go through a bunch of linear algebra exam 1 review problems and solutions. For the most part focused on low dimensional linear algebra. For example, you see here with number 1 that we have a problem with two-dimensional vectors that we can draw. We're also going to look at low dimensional examples of systems of equations, linear transformations, and coordinate changes. We will talk about the definition of matrix times a vector in the general case, and then we will look at a couple problems that are a little higher dimensional, kernel and image of a linear transformation from three-dimensional space to itself, and also a system of 3 equations and 4 unknowns. But mostly it'll be low dimensional here for exam 1. So let's go ahead and start with number 1. We see that we've got 2 vectors here, v and w, written as column vectors. V has components 3, -1, and w has components 1, 1. First part is to compute the vector v plus 2 times w and draw a picture illustrating how it arises from the geometric definition of vector addition, which is called the parallelogram law or the head-to-tail description. Part B, we want to compute the dot product v dot w. Part C, we want to compute the magnitudes of these vectors. And in part D, we want to find the angle taken to be between 0 and 100 degrees, 180 degrees between v and w, and ultimately write your answer in both an exact form involving an inverse trig function and approximate the angle to the nearest degree. So we want to do all those things, okay? We're going to need to draw a nice picture to get a good feel for what's going on. So let's carefully draw a rectangular coordinate plane. Let's also carefully mark off tick marks equally spaced on the axes. 1, 2, 3, 4, 5, etc. I probably could just focus on the first and fourth quadrants here because of the vectors themselves, 3, -1, and 1, 1, but oh well, I started it this way. Let's continue it this way. All right, let's go ahead and first compute v plus 2 times w before we try to graph things. So I take v, written as a column vector, 3, -1, and add 2 times w. 2 is the scalar times w. I need to multiply the scalar by each component. 2 times 1 in the first component and 2 times 1 in the second component gives you 2, 2. I now add these vectors component-wise. 3 plus 2 gives you a component of 5, and -1 plus 2 gives you a component of 1. All right, that is what v plus 2 times w is. Now let's try to draw a picture illustrating this, either again with the parallelogram law or the head-to-tail description. I'll do both. Okay, so v is a vector whose first component is 3 and whose second component is -1. If I put its tail at the origin, that means its horizontal displacement brings us over to 3 and its vertical displacement brings us down to -1. So v looks about like that when I put its tail at the origin. W is 1, 1. If I put its tail at the origin, it brings me right there, but I want to interpret v plus 2 times w, so I need to multiply that by 2. I need to scale it. 2 is the scalar that's going to make 2 times w twice as long as w itself, so that'll bring us to 2, 2. Let's emphasize that. That's 2w right there, and if you want, you can also draw w itself right there, like I did. Okay? What is well, let's do the head-to-tail description of vector addition first. The head-to-tail description is this. Take this vector 2w and translate it over so that its tail, the starting point of the vector, is at the head, the ending point of v, starting right here. It's got horizontal displacement 2, vertical displacement 2. If I draw that vector starting here, it's going to end right about there. This is not a perfect drawing. These are supposed to be parallel to each other, and you can tell they're not exactly parallel. It's going to bring us to an ending point at a point whose coordinates are 5, 1, as we found for the components of this sum v plus 2w. This is really another copy of 2w, and that means the sum, if I start its tail at the origin, is this vector right here. So that vector right there, that is the v plus 2w, and this head-to-tail description, again, takes the tail of 2w and puts it at the head of v, and once you've done that, v plus 2w starts at the tail of v and ends at the head of 2w. I can relate this to the parallelogram law as well. If I translate v over so its tail is at the head of 2w, it's going to look about like this. And if my drawing was perfect, that would be a perfect parallelogram, and your sum, v plus 2w, would go from this corner of the parallelogram to the opposite corner, as you see right there. Okay, good enough picture to get full credit for that. All right, on to part B. Compute the dot product, v dot w. That's pretty easy. This is part B. This was part A here and here. Those are both part A. Part B, v dot w, 3, -1, dot 1, 1. There's a formula for dot product that just says you add the products of the corresponding components. So that means, in this case, the product of the first components is 3 times 1. Add the product of the second components, -1 times 1. This gives you 3 minus 1, or 2. The dot product of v and w is 2. Okay? Dot product is also called scalar product. It also always gives you a number. What is the dot product good for? Well, one thing it's good for is finding magnitudes. Another thing it's good for is finding the angle. We'll do those things in parts C and D. Let's go ahead and do part C next. The magnitude of v is also related to dot product. I don't need answer for B. I'll use that in part D, but we do need these magnitudes also for part D. The magnitude of v I could write as the square root of v dotted with itself. You could also think of it in terms of the Pythagorean theorem. You dot v with itself, you'll get 3 times 3 plus -1 times -1, 3 squared plus -1 squared. That's going to be square root of 10. That's the magnitude of v, a little bit bigger than 3. The magnitude of w is going to be the square root of w dotted with itself, also with the Pythagorean theorem. You're going to get the square root. Okay, that's not w. This was w. Careful. You're going to get the square root of 1 squared plus 1 squared. Square root of 2. Okay, about 1.4. All right, now we found those magnitudes. We can now move on to finding the angle between the two vectors. It's based on the relationship between dot products and angles given by this equation. V dot w can also be found as the magnitude of v times the magnitude of w times the cosine of an angle between them. And we can take the angle to be between 0 and 180 degrees. You can solve this equation for the angle by dividing both sides by the magnitude of v and the magnitude of w, and then taking the inverse cosine of both sides. Theta is the inverse cosine of v dot w over the magnitude of v times the magnitude of w. Okay? You need to know that the input for the inverse cosine, also called the arc cosine, is going to be between -1 and 1. There's something called the Cauchy-Schwarz inequality that will guarantee that, even in higher dimensions. And now I can just plug in the numbers I found. V dot w was 2. The magnitude of v was square root of 10, and the magnitude of w was square root of 2. That's fine as an exact answer. It can also be written as inverse cosine of 2 times square root of 20. That's also fine as an exact answer, because square root of 10 times square root of 2 is square root of 20. I could also, if you want, rationalize the denominator by multiplying the top and the bottom of this by square root of 20. I get 2 square root of 20 over 20. If I do that, that will simplify to square root of 20 over 10. And this can be further simplified to, oh, what fun. Square root of 20 is the same as square root of 4 times square root of 5. In other words, 2 square root of 5. And the 2 and the 10 can cancel to give me ultimately square root of 5 over 5, it looks like. Or 1 over square root of 5. There's so many ways this can be written. I don't care. Any of these things is okay. I just wanted to illustrate that they are all valid answers. Let's go ahead and now approximate this. I think I am in degree mode here already. Yes, I'm in degree mode. We're going to approximate this to the nearest degree. So we do inverse cosine of, I'll just do it as 1 over square root of 5, is about 63.4 degrees. To the nearest degree, that's 63 degrees. And if you want extra confirmation that it's all right, I could also, for example, do inverse cosine of, let's pick this one, 2 over square root of 20, which I could have simplified, I guess, from that form right away. Oops, that's not right. Inverse cosine of 2 divided by, inverse cosine of 2 divided by square root of 20. Yeah, okay? And if you had it in radian mode right away, you'd want to convert it to degrees by multiplying by 180 over pi. All right, that's kind of fun. Next problem doesn't seem like a typical linear algebra problem. However, I like to put it on my first linear algebra exam because one of the main applications that I like to look at with my students in linear algebra is difference equations, where you've got a vector on one side times a matrix and another vector on another side. You don't see any vectors or matrices here. You see a scalar difference equation. But we need to start simple and solve a scalar difference equation before in later exams we can do more complicated difference equations with vectors and matrices. So it's this thing, yn equals 3 times yn minus 1. The next value of y is 3 times the previous value of y is the way to look at that. That's called a difference equation. Really? Even though you don't see any difference? Well, you could write it like this, yn minus 3, yn minus 1 equals 0. Then you'd have a difference. It's a discrete form analogous to a differential equation. I'm actually teaching this as part of a differential equations in linear algebra course, and I like relating the topics. The initial condition is that y sub 0 equals 5. Part A, write down the values of y1, y2, y3. You just got to use the difference equation and the initial condition. Part B, write down either by memorization or pattern recognition a formula for yn in terms of really y0. In general, you might have just an arbitrary y0, but we have a particular y0 here, 5. Okay, this is pretty straightforward. Just plug and chug. y1, for example, will be found from this equation when n is 1 to be 3 times y0, but y0 is 5, and so this becomes 15. y2 is going to be 3 times y1. I'm using the difference equation when n is 2. So that's going to be 3 times 15. That's going to be 45. And then y3 is going to be 3 times y2. Use the difference equation when n is 3. So that will be 3 times 45, and that will be 135. Okay? So what's the general pattern? If it's unclear to you, you could sort of keep iterating the difference equation, so to speak. I could say yn is 3 yn minus 1, which is 3 times yn minus 2. In other words, 3 squared times yn minus 2. Then you'd use it again. You'd get 3 squared times 3 times yn minus 3. In other words, 3 cubed times yn minus 3, etc. And the pattern here seems to indicate that if you go back to y0, which would be y sub n minus n, the thing you subtract here matches the power there. It looks like we're going to have 3 to the n times y0. And since our y0 is 5, that's going to be 5 times 3 to the n. You can always check this by plugging a number in for n. For example, n equals 3. You're going to get 27 times 5, and yes, 27 times 5 is 135. So there is your general formula. You don't have to do all this stuff to figure that out. You might have been able to just think about it with these numbers here, but that is the answer. That is the solution of the initial value problem. We found a direct formula for yn rather than a recursive formula or difference equation. It's good. We've solved the difference equation that way. All right, on to the next problem. The next problem is a general kind of problem, a description of what it means to multiply a matrix times a vector. So this is, in theory, a possibly high-dimensional problem, though it is abstract, so you don't actually have to do any calculations. But I really try to emphasize this as one of the most important concepts in linear algebra right here. It's the key to understanding the connection between linear transformations and matrices, to understand this right here, and other stuff as well. So A is an m by n matrix. That means it's got m rows and n columns. Watch what I'm doing here. If m, for example, is bigger than n, you're going to have more rows than columns. It's going to be a tall and skinny matrix. If m is smaller than n, you're going to have fewer rows than columns, and it's going to be long and skinny sideways, like that. And x is a vector in Rn. This funny symbol means Rn. It's n-dimensional space. It's the set of all column vectors that are n-dimensional, that are n by 1 matrices, if you will. M and n are arbitrary positive integers. Part A, describe in your own words or symbols the definition of the matrix vector product A times x. Okay. What I'm going to do is I'm going to go ahead and write an equation for it, essentially. But my students, I'm telling you, you should be able to describe this equation in words, and I will verbally describe it as I write it. Okay. Part B, what is the nature of this product? In other words, is A times X a matrix with more than one column, or is it a column vector? What are its dimensions? That kind of thing. Okay. Here's a nice way to think about it. So you got A times X there. Okay. A has got m rows and n columns. It's m by n. X has got n rows and one column. It is a column vector. An n-dimensional vector could be thought of as a column vector, or it could be thought of as a row vector, but we are thinking of it as a column vector because it's more convenient in terms of A times X. A has n columns. We could symbolically represent those columns as vectors, as m-dimensional vectors. Call them A1, A2 through AN. There are n of them, 1, 2, 3, etc. through n, and they are all m-dimensional because there's m rows in A. If it helps you to pick, m to be 3 and n to be 4, go ahead and do a side calculation or example where you're thinking about that. These are all in elements of Rm. That's worth writing. These are all in Rm. They are column vectors that are m-dimensional with real entries. I'm multiplying this times the vector x. It's an n by 1 column vector. These things that I'm going to put here are numbers. Notice I'm not putting the little half arrow above them. They are numbers, not vectors. They are the components or coordinates of the vector x. And there are n of them because this is an n-dimensional vector. It's in Rn. And what I always emphasize, and what many textbooks emphasize, excuse me, is that this product, by definition, here's the key, is a linear combination of these columns of the matrix capital A with these components of the vector x as the weights, the coefficients in front of the vectors, the scalars. In other words, the answer is the scalar x1 times the vector a1 plus the scalar x2 times the vector a2, etc., plus the scalar xn times the vector an. And because the number of components of this vector, n, matches the number of columns of capital A, n, this makes sense. There are n terms in this sum, n terms in this linear combination. The x's are called weights or coefficients. They are scalars, numbers in front of the vectors. Each one of these terms is a scalar times a vector, meaning each term is a vector, right? Because scalars times vectors are vectors. And each one of them is m-dimensional, m-dimensional. These are all in Rm. And therefore, the answer is a vector in Rm. Okay, so this equation represents answers to both questions. I'm describing with equations, but I verbally described as well. And my students, you should be able to give a purely verbal description if I asked you of this matrix vector product A times x. And as far as its nature goes, I mean, yeah, you could call it a matrix, but it's got one column. It's a column vector, really. It's an m by 1 column vector. An m by 1 column vector. It's a vector in m-dimensional space. Okay? Really, really key to understand that abstract idea. Okay? That's what it's all about. And I think I will come back to this in particular examples like even this one to illustrate it. Well, it's so important. Okay? This next problem. Find the solution of this following linear system of 2 equations and 2 unknowns and geometrically interpret the answer. Not saying what geometrically means there, I guess. but it's the usual geometric interpretation. These are two equations that are linear in x and y. They're going to describe lines in the plane, and the key geometric insight is that the solution is going to be the point of intersection of these two lines. Let's solve this a couple ways. First way let's solve it will help us go to the geometric interpretation right away. I could take this system and solve each equation for y as a function of x. Okay, and that'll help me graph the lines. I mean, you can graph them without doing that, but it's kind of nice to. And it also illustrates one way to solve the system. So for example, I could, with this first equation, subtract x from both sides to cancel on the left, and then divide both sides by 2 to get a y on the left. I'd get y equals, if I subtract x, I'd get a minus x on the right. Divide by 2 gives me minus 1/2 x. I already have a plus 1 over there. After I divide by 2, I get a plus 1/2. This one, I think I'll imagine adding 3y to both sides, dividing by 3, or, well, maybe I should add 4x to both sides and then divide both sides by negative 3. Add 4x to both sides, I'm going to get a plus 4x over there, but divide by negative 3, I'll get a negative 4/3 x. And then 6 divided by negative 3 is going to be negative 2. Okay? So this is a line with a slope of negative 1/2 and a y-intercept of positive 1/2, and this is a line with a slope of negative 4/3 and a y-intercept of negative 2. I could draw those lines. The point of intersection will be the solution. I can also use these two things to help me solve. I can set negative 1/2 x plus 1/2 equal to negative 4/3 x minus 2. Maybe I should just double check to make sure I didn't make a mistake here. I think this is good. All right. And then I want to isolate x. So I think I'll add 4/3 x to both sides and subtract 1/2. I'll need to do 4/3 minus 1/2 as a little side calculation here because of the 4/3 there and a minus 1/2 there. Get a common denominator of 6. That'll be 8 minus 3 over 6 is 5/6. Does that seem right? 4/3 minus, yeah, I think that's right. 5/6 on the left after adding 4/3 x to both sides. Subtract 1/2 from both sides, it cancels on the left. Negative 2 minus 1/2 is negative 2.5. That'll be negative 5/2. Now multiply both sides by 6/5. X is going to be negative 5/2 times 6/5. 5's cancel. Looks like it's negative 6 over 2, which is negative 3. Nice number. And then use either one of these equations to find y, and they should give you the same answer. If I plug in y equals negative 3 right there, I get positive 3/2 plus 1/2 is 2. If I had done it here, I should get the same answer. Negative 3 there times negative 4/3 is positive 4 minus 2 is also 2. So the solution, the unique solution, is the point x comma y equals, x was what? Negative 3, y is 2. That's the unique solution. Let's graphically interpret this. And then I'll also show you the elimination method, which will generalize to higher dimensional problems. So again, a line with a slope of negative 1/2 and a y-intercept of 1/2. So something about like this, say. And this would be 1/2 here and a 1/2 here. And the other one's a line with a slope of negative 4/3 and a y-intercept of negative 2. Does that make sense? Okay, yeah, it's going to intersect over here. All right. I was thinking it was going to intersect over there. So negative 2 is maybe about like here or so. Slope of negative 4/3. We know they're going to intersect at the point negative 3, positive 2. Maybe somewhere around over here they're going to intersect. So something, I'm not drawing it super carefully. Something about like this is your geometric interpretation of the unique solution. This line is the same as the line for the original equation. This one, original first equation, this one for the original second equation. Okay, so that's a geometric interpretation not drawn real carefully. Let's do elimination, and let's do it with matrices. An augmented matrix. Let's take the coefficients of x and y and make them the numbers in the first two columns, 1, 2, -4, -3. And then the right-hand side numbers goes in the last columns, 1 and 6. And I like putting an extra dashed line in here to emphasize in my own mind, for my own benefit, that this is an augmented matrix. These numbers represent right-hand side numbers there, to the right of the dashed line. I want to get this to the reduced row echelon form. I need to do elementary row operations to do so. I'm hoping typically what's going to happen is I get a 1 here, 0 there, 0 there, 1 there. So 1's on the diagonal, and then whatever comes over there are going to be my answers. Evidently, it's going to be -3 and 2. This is analogous to multiplying equations back up here by constants and adding to other equations. The row replacement operation is the one that's the most commonly done, especially when you got a 1 to start with. I'd like a 0 below there, so I'm going to multiply row 1 by 4, add it to row 2, and put the answer in row 2. Symbolically, I could write 4r1 plus r2 goes in r2. The first row is going to stay the same. Second row is going to have a 0 there. I multiplied 1 by 4. 4 plus -4 is 0, so that's why I put a 0 there. I got to do it to the other ones too. 2 times 4 is 8. 8 plus -3 is 5. 4 times 1 is 4. 4 plus 6 is 10. Right? So I got a leading 1 in the first row and a 0 below it. That's good. In fact, this essentially is in echelon form now, but not reduced row echelon form. It's in row echelon form. I'd like to get a 1 there. I mean, I can solve it without doing that, but to get it into reduced row echelon form is a good habit. So the next row operation, I'm going to multiply row 2 by 1/5. 1/5 times row 2, answer in row 2. That's an allowed row operation. To get a 1 here and a 2 there, put my dash lines in, keeping the first row as is. And now I've got a leading 1 there. I'd like to get a 0 above it. So now I'm going to multiply row 2 by -2, add it to row 1, and put the answer in row 1. So I will get a 0 there. This is the typical kind of form. Not always. Sometimes you get a 0 here. And then what happens up here? Multiply row 2 by -2, add to row 1. And 2 times -2 is -4. -4 plus 1 is -3. There we go. There's our answers. This corresponds to x equals -3 from the first row and y equals 2 from the second row. We are matching the other solution we got. One other solution method would be to solve, say, this equation for x as a function of y, and then substitute that in place of x there and solve for y, and then find x. You get the same answer. All right, this problem. Suppose that based on xy rectangular or Cartesian coordinates, a line has this equation. Suppose further that a transformation to a new UV skew coordinate system is given by a linear transformation defined by these linear equations with inverse linear transformation given by these. You're just trusting me on all this, that we're going to just use these equations, and these are inverses of each other. Writing these in scalar form instead of matrix form. We will look at linear transformations in matrix form. Oh, that reminds me, but I did want to think of this in terms of a matrix multiplication as well. I will come back to that. This problem is easier than it looks, okay? All you have to do, really, this stuff is just background here. All you have to do is take these equations and substitute back up here and then simplify. Since I said find an equation, you actually don't even have to simplify, but I could ask you to simplify. So replace y with 1/2 u plus 1/2 v. Replace x with 1/2 u minus 1/2 v. Add 1. Okay, there's an equation. Let's simplify. Multiply the 3 through. And probably good to say solve for v as a function of u. That's probably a good idea in the new coordinate system. And by the way, I'm not saying geometrically what's going on with this transformation. I think it is looking at it some sort of combination of a rotation and a dilation geometrically. Let's solve for v as a function of u. So let's add 3v to both sides. 3 halves v. 3 halves v plus 1 half v is going to be 2v. And I'm going to subtract 1 half u from both sides. 3 halves u minus 1 half u is just u plus 1. Now just divide both sides by 2 and get v is 1 half u plus 1 half. A different equation, but still fairly simple if I have not made any mistakes. So I'll try to put an annotation if I make mistakes. Hopefully this is good here. What's going on here? You know, this line has a graph that's going to look something like this. In some new UV coordinate system, which is somehow rotated and dilated, I don't know, it might look something like this or something with u and v axes. I'm not being real precise. This same line would have a different equation, okay? Is the big idea behind this, and it's a point I really like to make when I teach linear algebra, is to emphasize that. Just the basic idea right now, we'll get into a lot more details later. All right, 6 here. Excuse me. Now we're going to get into, well, with this problem, a little higher dimensional situation. A linear transformation from R3 to R3. Though the next problem is going to be back to lower dimensional, but then the final problem is going to be higher dimensional again. Linear transformation from R3 to R3 defined by the formula, get this careful, T of x equals A times x. Oh, and I forgot about the matrix multiplication here. It's worth doing. This can be thought of, this system here can be thought of as a matrix multiplication. The left-hand side can be thought of as this matrix times this vector equals this vector. This is the coefficient matrix of that system. Because, and these are the column vector, and there's your output vector, so to speak. Because if you think of this as a vector here, it can be written as a linear combination, x times 1 negative 4 plus y times 2 negative 3 by what I talked about back up here. That's a linear combination of the columns of this matrix with the entries or components of this vector as the weights, as the coefficients. We're wondering, and we solve for x to be negative 3 and y to be negative 2, so that linear combination equals this particular vector right here with components 1, 6. And that has important implications for coordinate systems as well. All right, come back to this other problem now. T of x equals A times x. A is a 3 by 3 matrix, 3 rows, 3 columns. X is a 3-dimensional vector. The domain of this linear transformation is R3. Its codomain is R3 as well. A times x is going to be in R3 because the columns of A are 3-dimensional. I'm forming a linear combination of them. Part A, show details of how to use elementary row operations to help you describe the kernel of T, which is also called the null space of A. You can write it either way. In parametric vector form, show your work. Okay? What's the kernel of T? Same as the null space of A. It's the set of all vectors in the domain, which is R3, that get mapped to the 0 vector. The set of all x in the domain R3, here's the domain, such that T of x equals 0, which is equivalent to saying A times x equals 0. Okay, that's what the kernel of T is. You can also call it the null space of the matrix A. We're trying to solve a system of homogeneous equations where the right-hand side numbers are all 0, because it's important. That's the simplest kind of system to consider, and it always has at least one solution. Okay, the 0 vector is always a solution of a homogeneous system. So the kernel always includes at least the 0 vector. Does it include more? Little insight here. 3 by 3 matrix. Typically, if the entries of the matrix were random, the kernel of T, the null space of A, would be just the 0 vector. However, this seems almost magical. With these numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, it's going to turn out that the kernel includes more than just the 0 vector. I just happen to remember that. So that's why I went with that matrix. Okay? But to solve the problem, we need to do row operations with an augmented matrix and show details. I think with the very last problem we do, we'll just use a calculator to do the row operations. But here, let's go ahead and show the details. So I'm trying to get it into reduced row echelon form, where I have leading ones in each row. The ones in a given row, the leading one in a given row is to the right of any leading ones in rows above it, if there are rows above it. And every leading one has all zeros below it if there are spaces below it, and zeros above it if there are spaces above it. And what you typically get in the end with a situation like this is you get ones along the main diagonal there, and zeros under there, here, and these two spots would be zeros. That's what typically happens in this kind of situation, but it's not going to happen here. I want to get zeros below the first leading one in the first row. Multiply row 1 by -4. Add it to row 2. Put the answer in row 2 to get a 0 there. And also multiply row 1 by -7. Add it to row 3 and put the answer in row 3 to get a 0 there. The first row is going to stay as is. I know I'm going to get zeros here and here. The only work I need to do is in these spots, and actually I'm going to get zeros here and here, because I know when I multiply 0 by anything and add to 0, I still get 0. So the only work is to do is with these spots. 2 times -4 is -8, plus 5 is -3. 2 times 3 is 6. Excuse me. -4 times 3 is -12, plus 6 is -6. Just double check that. Okay, so we're doing -4. -4 times 2 is -8, plus 5 is -3. -4 times 3 is -12, plus 6 is -6. Now figure out what goes there. -7 times 2 is -14, plus 8 is -6. And -7 times 3 is -21, plus 9 is -12. And lo and behold, I do see these two rows are multiples of each other. That is going to guarantee all zeros in the bottom row here. But before we do that, let's multiply row 2 by -1/3. You don't have to do this first, but it just makes it a little nicer to get a leading one in that second row. A 1 there, a 2 there, 0. Before I do the row operation to get a 0 there, which will also end up giving me a 0 there. I could have done that step second. I could have got zeros here and here right away, but multiply row 2 by 6 and add to row 3 to get a 0 there. So 6 times row 2 plus row 3, put the answer in row 3, gives me a 0 there, but it also gives me a 0 there. That doesn't typically happen, but it does happen here. 6 times 2 is 12, plus -12 is 0. Keep the first two rows as they are. Now I have a row of zeros. That does happen sometimes. Sometimes you get 2 rows of zeros. This is row echelon form, but not yet reduced row echelon form, because I need zeros above any leading ones. This one doesn't have anything above it, but this one does. I need to get a 0 there. So my last elementary row operation, I'm going to multiply row 2 by -2, add it to row 1, and put the answer in row 1. I can quickly fill in a bunch of stuff here. The only work to do, actually you're going to get a 0 there. The only work to do is to figure out what goes there. I'm multiplying row 2 by -2, adding to row 1. 1 times -2 is -2, plus 2 is 0. 2 times -2 is -4. -4 plus 3 is -1. Okay, now it's in reduced row echelon form with a row of zeros. What that's going to mean is we're going to have what's called a free variable for the corresponding system. If I think of the components of x as being, say, x1, x2, x3, I could also use x, y, and z. Then x3 is a free variable. It's free to vary. It's going to be the parameter in the parametric vector form of the solution set for the kernel. You got to be really careful here. Here's a common place people make mistakes. You need to think about what are the corresponding equations here. If I'm using x1, x2, and x3, this first line means x1 minus x3 equals 0. The second line means x2 plus 2x3 equals 0. Get x1 and x2 in terms of x3. x1 will equal x3, x2 will be negative 2x3. Common mistake people make is because of the negative 1 and the 2 there, they think there should be a negative sign there and a positive 2 there, but that's wrong. You got to think of it in terms of a system of equations. So that's one form of the parametric form of the solution set of the kernel. But we want to write it in parametric vector form. We want to think of the solutions, elements of the kernel, as vectors. The kernel of T, which again is also called the null space of A, is the set of all vectors, three-dimensional vectors, where the first component is, say, x3, the second component is negative 2x3, and well, the third component is x3. The free variable is itself, as x3 varies over all real numbers. That's fine. You could also factor out the x3 and write it this way, as x3 varies over all real numbers. That is the kernel. Kernel of T, null space of A. It's the answer for part A. It is a one-dimensional subset of three-dimensional space through the origin. It's a line to the origin. In fact, all scalar multiples of this constant non-zero vector are parallel to it. As arrows based at the origin, they're all parallel. As points, the set of points is a line through the origin. One-dimensional. It's a one-dimensional, we call it a one-dimensional subspace of three-dimensional space. Because it includes more than the zero vector, the answer to the second question, is T one-to-one, is no, it's not. I asked for a brief explanation. What does one-to-one mean? One-to-one means distinct inputs give you distinct outputs. Not one-to-one means there are different inputs that give you the same output. There's infinitely many inputs here that get mapped to the zero vector. Infinitely many inputs that get mapped to one output, the zero vector. This is not one-to-one, it's infinity to one. It's very much not one-to-one. For example, T of 1, negative 2, 1 equals T of 2, negative 4, 2 equals 0, 0, 0 is a good enough reason. I can pick any scalar multiples of these. Just make them different, so you have two distinct things getting mapped to the same thing. So no, it's not one-to-one. Part C, describe the image of T, also called the column space of A, different names for the same thing, as a set of linear combinations. This would really be in parametric vector form as well, though you don't have to do much work to find it. What in the world? This gets back to the definition of matrix multiplication yet again. Image of T is the set of all outputs of T. It's the same as the column space of A, which by definition is the set of all linear combinations of the columns of A. When I form linear combinations of the columns of A, I'm describing A times X for various X's. That's the same as T of X for various X's. It's the same as the image, as X varies over all of the domain, all of R3. So what I'm trying to get at here is the answer for the image of T also called the column space of A, is the set of all linear combinations of the columns of A, with weights, say, x1, x2, and x3. x1 times the first column of A, plus x2 times the second column of A, 2, 5, 8, plus x3 times the third column of A, which is 3, 6, 9, as those three scalars, x1, x2, x3, vary over all real numbers. That's the answer, by definition. Does that mean it's a three-dimensional set? A three-dimensional subspace of three-dimensional space, which I guess would mean it's all of three-dimensional space? It's not obvious, but the answer is actually no. This, in spite of the fact that you got three parameters, is actually not a three-dimensional subspace of three-dimensional space. It's a two-dimensional subspace of three-dimensional space. Again, that's not obvious. Typically what's going to happen is it will be all of R3, but because the kernel was non-trivial, it included more than the zero vector for this 3 by 3 matrix, it's going to turn out that this is actually not three-dimensional. It's a two-dimensional subspace. Of R3. Again, that's not obvious, and I did not ask my students to say that in the problem statement. But it is true. It turns out the dimension of the image plus the dimension of the kernel, 2 plus 1 is 3, will always be the dimension of the domain, which is 3. And that's true even if the dimension of the domain were not 3, even if it were 4-dimensional or 5-dimensional or 2-dimensional, though this matrix would then change its dimensions if that were the case. Okay, that's a pretty fundamental theorem that we get to later. Two more problems. And I'm going to make the last one go quicker by using technology. This one says find a formula for a linear transformation from R2 to itself, so this is back to lower dimensional, that first rotates points or vectors 90 degrees clockwise, usually we do counterclockwise, about the origin, and then reflects points / vectors across the line y equals negative x. So this is the composition of two functions. And as far as where my students are at this point in the course, technically I'm teaching a differential equations and linear algebra course, we haven't talked about matrix multiplication of an arbitrary matrix times another arbitrary matrix yet. That's one way to solve this, and I will show it to you. But it can be done without thinking about matrices, though you do need to think geometrically about what's going on with these transformations. What I need to do is I need to think of T as a composition. First rotate, then reflect. So I need to find formulas for those transformations first and then compose them. So if I first imagine rotating, well, it's unfortunate that rotate and reflect both start with R. I'll call the rotation R. I'll call the reflection S. It's going to take an arbitrary point, which you can think of as a vector as well. Let me go ahead and write it as a column vector, xy. And if I'm rotating it 90 degrees about the origin, for this particular vector that I drew, it's going to look about like this. That's going to be R of xy, written as a column vector. And if you're careful in thinking about this, at least for this particular example, well, I've taught my students that if you rotate by negative 90 degrees, that what happens, or 90 degrees counterclockwise, what happens is you swap the coordinates and you put a negative sign in front of the first one. Here you swap the coordinates, the x and the y, and you put a negative sign in front of the second one, is the formula. And that certainly makes sense when you think about a particular vector like this. I mean, I made both components positive. In this picture, obviously, the second component of the answer has got to be negative, and the first component positive. Certainly not a proof that this formula works for any vector, but it turns out it does. You're trusting me on that. If I also think about another transformation that reflects points around that line, call it S, the line y equals negative x, it's this line here. Give me an arbitrary point slash vector xy. It's going to get mapped. This particular one that I drew is going to get mapped to something about like this. I could have drawn it here as well. That's going to be S of xy. And for reflecting across the line y equals x, you just swap x and y. What happens here when you reflect across the line y equals negative x? At least for this example, it seems like both components became negative. I think it's going to be this, negative y, negative x. You got to swap the coordinates and put negative signs in front of both of them instead of just swapping the coordinates. I mean, you could check that for other examples. Like if your vector were here initially with negative first component and positive second component, it's going to reflect to there. Still negative first component, positive second component. Let's just pretend it's the vector negative 1, 4 is going to get mapped to. Switch these around, 4, negative 1, and then negate them both. It's going to get mapped to negative 4, positive 1. That's going to be what that vector is right there. Ignore this. So, I mean, this is not obvious, okay? And maybe a little too hard for this kind of exam unless I'd done examples like this. It's tricky that this would be the formula for this. But these, I believe, are correct. And T then is going to be the composition of these. T of xy. Do R first, then S second. Rotate first, then reflect. So as a composition, that's S of R of xy. R of xy is y negative x. Goes there. S of y negative x swaps the components and puts negative signs in front of both of them. So in the end, it looks like the composition is x negative y, which ultimately is a reflection across the horizontal axis when you compose these. Take this vector, first rotate it, then flip it across the line y equals x, negative x. You're going to get a vector like that, which is the reflection of the original vector across the horizontal axis. Hey, cool. Just for fun, let's do the other direction. R of S of xy, it's not necessarily the same answer because function composition is not commutative. S of xy is negative y, negative x. Apply R to that. You swap the components and put a negative sign in front of the second one. Swap the negative x and the negative y around. Put a negative sign in front of the second one and simplify. Yeah, these are not the same. This is a reflection across the horizontal axis. This is a reflection across the vertical axis. So the order matters. This was not asked for, but it matters. In terms of matrices, it turns out a matrix for R, call it A. I'm not going to explain this, though you could think about it, why it makes sense based on what I've told you so far. Let's see, I got to be careful here. It's going to be first column of 0, negative 1, second column of 1, 0. A matrix for S, call it B, is going to be 0, -1 for the first column, -1, 0 for the second. The matrix for T should be B times A. Now, again, for my students, at this point, we haven't talked about general matrix multiplication. And I'm not going to explain this. I'm just going to do it. 2 by 2 matrix times a 2 by 2 matrix is another 2 by 2 matrix. The entry in the upper left corner is going to be the dot product of this row with this column. 0 times 0 plus -1 times -1 is +1. The upper right entry is going to be the dot product of this row with this column. 0 times 1 plus -1 times 0 is 0. Lower left entry is going to be the dot product of this row with this column. 0 plus 0 is 0. And the lower right entry is going to be the dot product of this row with this column. -1 plus 0 is -1. And yeah, this matrix would be the matrix for that formula right there. That will work. Okay, and again, I'm not explaining that, but if you want to take the time to think about it, you certainly could. All right, last problem. And to save time, we'll use technology. And in fact, I've even typed things into my technology ahead of time to save some time. Find a general solution of the following system of equations with 3 equations and 4 unknowns. As a linear transformation, the corresponding linear transformation, well, the matrix for this, the coefficient matrix, is going to be 3 rows and 4 columns. And that means the corresponding linear transformation is going to be from R4 to R3. If you want to think that way, my students, it's good to think about based on some reading you've done. We have not quite solved systems like this yet. You'd want to create an augmented matrix. The coefficient part, the first row is 1, -5, -9, 8. Second row is 0, 1, 3, -4. Third row is 0, 2, 6, -8. But it's going to be an augmented matrix with the numbers from the right-hand side after the dashed line, -7, 2, and 4. And you do want to do row operations on this to get it to reduce row echelon form, where you have a leading one in each row. The leading one in any given row is to the right of any leading one in a row above it, if there is a row above it. And there are zeros below and above any leading one when there are rows below and or above. But let's just use the calculator to get to the reduced row echelon form. I did pick things to work out nicely. Sometimes it doesn't work out so nice and you have fractions and stuff. If we go to matrix menu, second matrix right there on my calculator here, I've actually put this augmented matrix in matrix B. Here it is. It's a 3 by 5 matrix, the augmented matrix. 3 rows, 1, 2, 3, 5 columns, 1, 2, 3, 4, 5. The coefficient matrix itself is 3 by 4, but I need that last column for the right-hand side numbers. So I've typed 3 by 5, and you can check these numbers are correct. 1, -5, -9, 8, -7. On to the next row. 0, 1, 3, -4, 2. On to the next row. 0, 2, 6, -8, 4. Then we want to go back to the matrix menu and do math. And it's RREF, reduced row echelon form. Oops, I don't want it there though. Exit. Matrix, math, and you can actually go upwards to get there faster. A little bit. RREF. Back to matrix mode, the name B. There is a reduced row echelon form. It's not typical to get a row of zeros in this situation, but we happen to. Typically in this situation, you would not get a row of zeros, but sometimes we make matrices where that happens to test you on concepts. So trusting this, the reduced row echelon form is first row 1, 0, 6, -12, 3. Second row 0, 1, 3, -4, 2. Third row all zeros. And this is a consistent system because for this augmented matrix, we do have a 0 there, and there's not a leading 1 in this last spot. If there were a leading 1 there, it would actually be an inconsistent system because it would imply that 0 equals 1. No solution. Which could have happened, but I didn't make it to happen. All right. We're after solution set using what are called basic variables and free variables and parametric vector form like before. Describe the solution set geometrically. Is it a line? Is it a plane? What is it? Well, for one thing, it is a subspace of R4 because you got 4 variables to begin with. The domain of the linear transformation is R4, 4-dimensional space. So if it is a line or a plane, it's somehow sitting inside 4-dimensional space. It's a matter of, once again, being careful to write the corresponding system of equations down here. x1 plus 6x3 minus 12x4 equals 3. And by the way, because this is a non-homogeneous system, if this is a line or a plane, it's, yeah, I don't remember if I said the wrong thing a minute ago. It's not going to be through the origin, actually. And then the second line there, the second row is x2 plus 3x3 minus 4x4 equals 2. So we want to solve for x1 and x2 in terms of x3 and x4. x3 and x4 are going to be the free variables. They are varying freely. But once we've chosen them, x1 and x2 are determined. We call those basic variables. So let me just jump right away to the parametric vector form. These are going to be 4-dimensional vectors. x1 is 3 minus 6x3 plus 12x4. Careful, you got to subtract 6x3 from both sides and add 12x4. x2 is 2 minus 3x3 plus 4x4. And x3 and x4 are themselves. And these are free variables. They are free to vary over all real numbers. You can split this vector up into a linear combination of 2 vectors where x3 and x4 are the scalars in front of them, the weights. Look at what x, and also a constant vector as well. x3 is in front of a vector with components -6, -3, 1, 0. x4 is in front of a vector with components 12, 4, 0, 1. And yeah, there is a constant vector in this case where you've got no x3 or x4 by them, a 3 and a 2 and a 0 and a 0. Because of that non-zero constant vector in there, this is not going to go through the origin in 4-dimensional space. It is a 2-dimensional plane in 4-dimensional space, not through the origin. How do I know it's a plane as opposed to, say, maybe just a line? Because these 2 vectors are not parallel. They are not scalar multiples of each other. Somehow in 4-dimensional space, they're not going to be on the same line. And because of that, this is going to define a plane. This just affects how far the plane is from the origin, in a sense. If I take x3 and x4 to be 0, this vector / point would be a point in the plane. And it's non-zero, so it's not through the origin. These 2 vectors that are not parallel are also called linearly independent. Linearly independent. And that's why this is 2-dimensional. For my students, we haven't talked about linear independence yet in the DiffyQ with linear algebra course. If you're taking a pure linear algebra course, we probably have. And thanks for watching.